Hi guys! So for my engineering project, I'm going to be talking about bridges and forces. The first thing that I'm going to say that applies throughout this whole video is that bridges really rely on forces to keep themselves upright, which is why we have bridges and forces be a single unit and not just a forces unit and then a bridges unit or vice versa. So I'll start by doing off a little bit of review. There are a couple of different kinds of forces, and the ones that I'm going to talk about are the ones that we've learned about in class. First, we've got compression, which is pretty simple. Two things push against each other, right? Good. Next, we've got tension. Okay, they pull apart. Then there's bending, which is when pressure is applied to one side of an object and tension to the other. Okay, not too messed up, right? Let's continue. Then there's shear. Shear is kind of like compression inside out and messed up. Either two things slide against each other or one thing is pulled two different ways and slowly, or even for that matter quickly, is pulled apart. And the last one I'm going to talk about is torsion. Torsion is probably the most messed up of all of the forces because it's compression and it's tension and it's shear and basically it just twists around. It's a really weird force, but it ends up causing a lot of problems with bridges later on. So anyways, bridges! I'm going to start out by talking about some of the history of the bridge, which is long and complicated and kind of needs to be explained for this video to work. So some of the first bridges that we are really going to focus on are the post and beam bridges made by the Greeks. So a post and beam bridge is really just a really long slat of some material, in this case wood, over some type of posts, which are in this case boats. So the Greeks needed to get places easily and have a quick escape route so that their enemies couldn't cross over, and so basically they'd take their boats and put a piece of wood on over them. This was actually really easy because wood was everywhere, and I mean everywhere. You could just cut down a tree and stick it on top of your boats as you floated down a river to get across. This was also a lot more stable than just hopping from boat to boat because, first, that's hard. Also, if it's a big enough river and you've got these small little boats, you're probably going to need a lot more boats than you have. So yeah, the Greeks used post and beam bridges, which worked fine because they were cheap, easy, and also they could run away really easily and their enemies got stuck on the other side. But then came the Romans, and those guys had much bigger armies, and it was just a pain to be getting their armies across rivers on tiny little pieces of wood. So they built stone bridges, because the Romans needed to show these people that they were a part of the empire, and also not have to keep remaking the bridges, because stone was a lot sturdier. Basically, the empire worked easier with arch bridges because while wood could be put together and on top of each other, stone was a lot sturdier and more permanent and definitely did not require as much maintenance. So basically, in an arch bridge, there are all the rest of the pieces of the stone, which are shaped so that they fit the arch, and then there's the keystone. And the keystone is the only thing that keeps the bridge from completely collapsing. Without the keystone, the whole bridge falls down. So here's how it works. The arch bridge is built in a ditch or a river, so there is ground below it and next to it. When someone or something is placed on the keystone, it pushes down. This pushes on the other pieces, pushing down and out to the next stone and keeps pushing until it gets to the ground. Here it tries to push both down and out on the ground below it and to the side of it, and so it puts all of the pressure on the ground, which provides resistance, pushing back so it is pushing equally on both sides of the stones. This actually strengthens the bridge, so stepping on an arch bridge actually makes it stronger. This force is what that keeps the bridge together is compression, and so the bridge only stays together because of compression. By the way, there's a super cool arch bridge that I found, which is basically 3 arch bridges stacked on top of each other. It's called the Pont du Gard, and it was built a little less than 2,000 years ago in France. It looks really cool, and I'm not sure if you could just walk on one layer of all of them, but it looks pretty neat. Okay, so to continue, later on, truss bridges started to be made. Truss bridges are so strong for some of the same reasons that arch bridges are, because they distribute the weight equally over the whole shape. When you push on one of the triangles, the compression force wants to go down the direction you're pushing. But when it pushes on top of one of these triangles, it has to go down, but there are 2 paths to take both ways. So it pushes both ways, spreading out the force between the 2 different sides. This then pushes down on the side below the first 2 and spreads it out over the whole triangle. Basically, the same thing happens when you push on the upside down triangle, except it divides the force over 2 triangles instead of 1. A truss bridge spreads out the pressure over the entire bridge. And about the same time that truss bridges started to be made, people started to use cast iron for their bridges. Cast iron formed when you melted down iron, poured it into a mold, and let it harden. It seemed like the perfect material to be making bridges out of, but They figured out pretty fast that cast iron was really brittle and didn't bend or hold well under weight. Let's just say things didn't go very well with a few cast iron bridges and they had to move to a new material. As a side note, even now there doesn't seem to be a very great bridge building material. The cheap ones don't bend very well or are not sturdy and require a lot of attention, and the ones that work pretty well are expensive and harder to build with. Even now, there's still not a best material to build out of because they all have different strengths and weaknesses. So anyways, people were trying to find a good way to make bridges because it was getting harder and harder to do post and beam bridges over long distances like over bays and really, really big rivers. The beam bridges just weren't stable enough, and for obvious reasons, they couldn't make an arch bridge. So a couple of guys came along in California and decided that they really needed a bridge over the San Francisco Bay because it was a really long trip from one side to the other. They hear about this bridge that they've been building out in Europe that holds itself up using the ground, and it can go over really long distances. It only used tension to keep itself from falling down and was apparently very, very strong. A suspension bridge works by using tension to keep itself upright. By the way, that's what this bridge is. Without any of the cables, it would just be a regular post and beam bridge, and a really bendy one at that. But with these cables, it keeps itself from bending. First, the cable on top is attached to the land so it stays in place and doesn't come apart. It has to be solidly in place, and this is why there can't be more than 2 towers in the suspension bridge. Then the wires pulling on it keep it in place, as well as pulling up on the beam and counteracting any bending forces that might come from something being on it, breaking the bridge. This keeps the bridge much stronger than a post and beam bridge ever could be with such a long span. Oh wait, did I not explain what a span is? Oh, okay, so a span is the distance between supports on a bridge. Suspension bridges have the longest spans, beam bridges have the shortest. It all depends on how strong the bridges are. But anyways, the guy with the idea for this new bridge was named James Wilkins, and he had been an engineering student before he became a journalist, so he knew this sort of thing was possible, even though it would be really expensive. It was supposed to cost $100 million, but San Francisco's head engineer looked into it and found that Joseph B. Strauss, an engineer who also happened to be a poet, said that he could find a way to make it less expensive, like he cut down the cost by almost a quarter of the original price. So, after a few years and a little setback that we know as the Great Depression, the bridge was finally funded. Yay! Actually, it went pretty well. Joseph B. Strauss even wrote a poem about it. It was pretty cool. Here's a quote. "Ask of the steel, each strut and wire, what gave it force and power." He actually seriously believed that he could build this bridge, even though it took a lot of effort and a lot of time. And it seemed pretty much impossible. He was seriously invested in it, enough that he wrote a poem over it. I think that's actually pretty neat. Also the fact that he's an engineer and a poet at the same time. Okay, so now to move on to a less successful suspension bridge. The Tacoma Narrows. Pretty much, they built the suspension bridge, right? And they figured it would work out because most suspension bridges have been pretty successful so far. But then it started to twist, and twist, and twist. Eventually, after everyone was evacuated, the bridge tore itself apart. Luckily, the only casualty was a 3-legged dog, and that's probably, seriously devastating, but seriously, it's a dog. Anyway, this poor bridge tore itself apart because it caught the wind really well, which is not something you want a bridge to do, because strong bridges like that are going to be strong in compression, not tension, because they're mainly made of asphalt and concrete. So when it bends, it can't handle all of the pressure, and it breaks. So people made bridges that didn't catch the wind as well as the Tacoma Narrows from then on out. Finally, we'll talk about cable-stayed bridges, which are quite a bit less complicated than suspension bridges. They were actually built in the 1800s, and they're pretty simple. So this is what a cable-stayed bridge looked like. There could be as many posts as you want, but I'm going to start with 2. As you can see, the wires are attached to the poles. They're also attached to various places on the bridge. These cables are also strung very tightly, and so tension is at work, and the cables on both sides of the post are pulling it to the side each way, putting equal force on each side of the post, making the 2 forces cancel out. It's also being pulled down by gravity. But because of this tension on both sides of the post, it strengthens it and allows the post to stand up by itself and be less bendy. There are a lot of cable-stayed bridges. Even though they don't have nearly as long of a span as suspension bridges do and aren't nearly as strong, they're still pretty strong and a lot less expensive. Actually, while suspension bridges might seem like the best type of bridge all the time, they actually wouldn't work very well in some situations. Would you really want a suspension bridge over a smaller river? It would be expensive and impractical and definitely not easy to build. So really, it just depends on the situation and your price range. Also, because forces, and I haven't talked about them much, here are a few interesting facts about forces. When two things push against each other, compression, the denser one goes down. These things don't have to be particularly dense to even do so, just exist. And a lot of the forces can be demonstrated in tectonic plate boundaries. Two plates can come together, compression, they can rub against each other, shear, and they can pull away from each other, which is tension. They're not in the same object, so I don't know if that actually works. Don't quote me on that, but I'm pretty sure it's tension. So yeah, thanks for listening to my rant about bridges and forces. Hope you enjoyed!